everybody. Now let us continue our discussion further into this area of supramolecular reaction vessels. So in the previous lecture we looked at the enantioselective transformation which was achieved using Fujita's octahedral cage, where the cage has been modified by bringing in a chiral center in this particular cyclohexyl part, and because of the presence of the chirality in this fragment, the overall cage gives it the necessary chiral environment, and this facilitates this is the first example of a coordination cage which is applied for an enantioselective reaction, and which allows for the 2+2 cycloaddition reaction using this set of reactants. So this having achieved this success with supramolecular cages, people now decided to make supramolecular reaction vessels or these kind of nano cages of bigger dimensions, and which has also got broader architectures. For instead of looking at triangles, people started looking at extended triangles, looking at prismatic cages, looking at larger size prismatic cages, looking at square barrel like structures by modifying the ligand, so backbone. So the modification of the ligand backbone became an important prerequisite to form these kind of 3D barrels which are having more surface area available for effective encapsulation of the guest or the substrate molecules to achieve the desired transformations to the products given a set of reactants. So now let us go to the next molecular barrel. Molecular barrel, which is actually a 3D barrel, and in this regard the following ligand has been taken. So this particular ligand has been considered. So now we have got these donor nitrogens which are available. So we have got 1 2 3 4 5 1 2 3 4 5, okay, and then these are the ones which can coordinate to the palladium centers, okay, and the palladium part has got this particular arrangement. So we have got the palladium center which is the 2+, and this will lead to the formation of a barrel like structure where we have got so we are now going to have, so this can be equivalent to where you can have the coordination from palladium. So we can have 1 2 3 4 5 6 So we have this particular ligand which is called the tetraimidazole based tetraphenyl ligand, and it forms these kind of 3D barrels structures, where now you can see these are the large pi surfaces available for interacting with the reactant molecules, and these have got large pi surfaces areas, and the reactant molecules can now enter, and we can have chemical reactions which can take place in these 3D barrels. And this particular 3D barrel, which I am referring to as H now, so you can see here that there are this particular surface is there, this particular surface is there, and the back surface is there. Okay, so we have these 3D barrel which is used for the synthesis of xanthenes and tetraketones using this 3D barrel as a supramolecular catalyst. Okay, and in this case, this is a case of homogeneous catalysis. So what are the reaction conditions? Now we are going to consider the reactants here. So this is one reactant plus this is the other reactant, and in the presence of this molecular barrel H 5 mole % in water, it gives rise to this product. So this is the tetraketone, but it also forms the corresponding xanthene. It forms the corresponding xanthene. So here we have got the naphthyl ring. So this is the xanthene, and this happens because of the intermolecular cyclization, and the water molecule which is formed in this reaction can easily be expelled because of the hydrophobic cavity. So that drives the reaction towards the right hand side. And because we got both the products, the idea was to now obtain complete conversion of tetraketones to xanthene, and then the reaction was performed at 60 degrees centigrade only, that is at a relatively high temperature, and that led to the formation of 90% xanthenes. It is also important to keep in mind that that during this reaction, the anion is generated at this particular site, which actually performs a reaction, the nucleophilic attack at the carbonyl reaction center. So these kind of anionic centers are also stabilized by interaction with palladium 2+ centers, which are present in these 3D barrels. So these anions can get stabilized in the 3D barrels, and then the reactivity is enhanced by reaction with the electrophilic center. And it has been observed that this particular reaction does not take place in absence of catalyst. So again demonstrating the versatility of this particular 3D barrel structure. So now you have modified the ligand backbone by making this tetraimidazole based tetraphenyl ligand, this particular scaffold which facilitates this reaction. Keeping this in mind, further modification was done to this barrel like structures, where now people modified the ligand backbone further. So they were now able to make this particular barrel. And here we have got so this particular ligand was used, and then with ferrocene and we have the connection to PPH2 palladium center OTF twice, and in the presence of dry nitromethane 3 hours 50 degrees centigrade under nitrogen atmosphere, we were able to get this tetrafacial molecular barrel structure. And this tetrafacial molecular barrel structure, now you can see that there are large pi surfaces, and therefore it was useful. We call this barrel as G. So this barrel G catalyzed the intramolecular Diels-Alder reaction of, if there is an intramolecular Diels-Alder reaction, let us see what the reaction happens now. So we have this particular substrate so we have the dyne part here, so you can see very clearly that we now have the positioning. We have this 4 pi electrons, we have the 2 pi electrons, and they are in the relative proximity of each other, so that they can undergo in the presence of 10 mole % of the reaction barrel G, and when heated it will give rise to the desired product, where you will now have the dimerization taking place, and it will give rise to the so you will have hydrogen here, you will have the hydrogen here, so you will have the cyclization here, and then this will lead to the formation of the product. So you will see that at this particular juncture the 4+2 cycloaddition reaction takes place. So once we have the cycloaddition, the product is formed, and we have this cis fused product. The transfused product is also formed, but it is a minor quantity. So, when you take this substituent, that is the benzylidene barbituric acid, and you have the reacting groups which are in proximity to each other, it gives rise to the intermolecular Diels-Alder reaction, and the rate of this reaction is 7-fold higher in comparison to the reaction when no catalyst is there. Okay. So, this again demonstrates the relevance of the molecular barrel. And another interesting example we can take, where we can consider a multi-component sorted, self-sorted palladium 7 nanocage. So, now we are going to much different kind of barrels of different architectures to achieve this particular formation of this PD7 nanocage. We have considered now plus we now consider so we now consider this one. This is, and then we consider the corresponding N So, we consider this ligand as TIM, we call this TIMB, we call this TIMB is actually the 135 tris 1-imidazoyl benzene, and TIM is 1245 tetra bis imidazoyl benzene. So, this is TIM. So, it forms a barrel like structure, where the composition of the barrel is we have the palladium 2 plus, which are 7 units, we have TIM which is 2 units, and TIM that is 2 units, total NO3 14.20 water. So, this represents a triangular kind of a geometry, this represents a square kind of a geometry, and this I will represent in this way. And now I need to stitch them all. So, we can do this in the following way. So, these are the two stitching of the square surfaces, and now I can further stitch the triangle here, and there is another triangle which is stitched here, and we can have the palladium centers 1, 2, 3, 4, 5, 6, 7, and this is also I need to check, sorry, there is a slight correction here. So, we can now have the stitching here and here. Okay. So, this is a stitching. So, 1, 2, 3, 4, 5, 6 and 7. So, you can see that it forms this kind of a boat like barrel structure. So, this nice kind of a boat like barrel structure is formed where you have these triangles and here you have the squares, and this kind of a boat like barrel is referred to as a nano reactor, and nano reactor has been utilized this molecular boat to perform Knoevenagel condensation reaction with this particular molecular barrel. I call it as F, and for example, we now studied the condensation reaction of with aldehyde. We take 10 mole percent of of F in the presence of water 72 hours at room temperature. We get the product okay, and AR here can be phenyl, naphthyl or benzene. So, we are able to achieve this Knoevenagel condensation reaction in the presence of this molecular barrel which we refer to as a nanoreactor, and this reaction takes place in quantitative yields to give you the desired products. So, I hope I have been able to impress upon you the importance of supramolecular reaction vessels and in enhancing reactivity profiles, and these being very well exemplified cases of supramolecular catalysis. The next topic we would like to continue here further is we now extend our understanding of supramolecular chemistry to probing photochemical reactions and in the solid state in particular, and also compare the photochemical reactions involving supramolecular chemistry the different non-covalent interactions in solutions as well. So, now we go on to the topic of supramolecular photochemistry, and we have given some introduction about supramolecular photochemistry during a discussion on crystal engineering, and so we are aware that utilizing strong hydrogen bonds, it is able to we are able to pre-organize the substrates in a certain way so that cycloaddition reactions can be performed in crystals as well. And we would now like to continue an extended argument further. So, to start with, there is a relevance of doing supramolecular chemistry in solids. Solids give the necessary environment to the molecules by which specific reactions and specific transformations can be achieved, which otherwise do not happen in the solution state. So, there are certain photochemical reactions which can go to near completion, provided the reactant molecules are brought into the right orientation and the right kind of environment is given to them, such that after the reaction takes place, if there is any change in the shape, then there must be sufficiently free volume also available for the product to be effectively included within the crystalline environment, because here we have got a very tightly packed crystalline environment, and the formation of the product can lead to changes in the three-dimensional structure that might need more space, and therefore the necessary volume must be available, otherwise it will be a highly strained system and the product formation might not take place. So, and also Another very important advantage of the solid state environment is that when there are certain reactive molecules, for example, certain molecules which form free radicals in the gas phase, and these free radicals are very reactive, they can also be stabilized inside these kind of solid state environment or supramolecular cages, where the lifetime of these free radicals can be increased. And because the molecules are now able to come into close proximity, we can actually promote phosphorescence and other luminescent processes of the molecules in the solid state, and these can be observed at room temperature. And also we can bring in chirality into the molecule, because we are now able to perform the cycloaddition reactions by making prochiral centers come close to each other, doing the chemical transformations and creating the necessary chirality in the final structure via this solid state environment. So to start with, if we consider a molecule AB which is having a double bond, and if we shine light, then in solution the large number of isomers can form. For example, we can have this as the product, we can have this as the product, or we can have this as the product. Like that, there are 12 possibilities which exist. So there is no control over the reaction, because you can have dimerization in so many possible ways. And but now if you want to control this particular dimerization process in a specific way, what was proposed by G. M. J. Smith was that when you take cinnamic acid and then you photo irradiate in the solid state, then it can lead to the formation of the centrosymmetric dimer, which is called alpha tetroxylic acid. Here the separation between the double bonds is 3.9 to 4.1 angstrom, 3.6, the distance is less. On the other hand, when you have the beta form, because this compound exists as different polymers, in the beta form, when the separation is 3.9 to 4.1 angstrom, it will give rise to the beta tetroxynic acid. And here you can see that there is a mirror symmetry which exists in the final product. And if you have the gamma form, then the separation between the double bonds is longer, and therefore no reaction takes place. Therefore this particular form is photostable. So these were the conditions which were very well described by G. M. G. Smith as necessary conditions to achieve a solid state dimerization process. That means we can have a crystalline environment, we can have three-dimensional structures, or we can have layered structures where the double bonds are actually not in proximity to each other. So if they are not in proximity, they will not dimerize. So if the arrangement of the double bonds in the crystal is such that they are not within a certain distance or proximity, then these reactions don't take place. So then the thing was that, okay, can we now modify the solid state environment? The modification of the solid state environment was done by co-crystallizing these kind of molecules which have double bonds but do not have the pre-organization or the pre-orientation to bring the double bonds close to each other. So can we now utilize some templates which form strong hydrogen bonds with these molecules which contain double bonds and bring them into close proximity so that we can achieve the dimerization process. So to understand this particular case, first we will consider the molecule trans 1,2 bis 4-pyridyl ethylene, which we also refer to as 4,4 prime BE. Okay, and it has been observed that bis pyridyl ethylene, that when it is photochemically irradiated in solution, it leads to cis isomer. So essentially they exist trans cis isomerization in solution. However, when you take this particular solid and photochemically irradiated, there is no dimerization, because the double bonds are not in proximity to each other to react. So let us take this particular example. So they have to come close to each other for them to react, and this arrangement is not there in the case of the parent compound. That means in the parent compound it essentially has the gamma type of packing, which we saw here, that is the gamma form, this type of packing where the distances are very long, and therefore the dimerization does not take place. So here the distances are greater than 5.7 angstrom, and therefore no dimerization takes place. However, if you now co-crystallize this particular compound with 1,3-dihydroxy benzene, then we are able to bring them into the position. So OH, so now we have the hydrogen bonds. The same thing can happen here. We can now bring in the hydrogen bonds here. So this dihydroxybenzene now brings these molecules close to each other. The distance is around 3.7 angstrom, and therefore now when you shine light, they undergo photochemical dimerization, or they undergo the 2+2 cycloaddition reaction. Along the same lines, just to like similar to that of this dihydroxybenzene, people have also used thiourea as a template as well. So with this we will stop this lecture. In the next lecture we will take up more examples related to supramolecular photochemistry. Thank you.